Good morning, and for the last time, welcome to Foundations of Algorithms. I'm truly happy to see that so many of you have made it here on week 12. As always, today is going to be no different. We will start with our historical figures, and today we have two people who will be the subject of a lot of our lecture today. This is Stephen Cook and Leonid Levin. Now, Stephen Cook was born in 1939, and Leonid Levin was born in 1948 and is of Soviet Jewish origin. Just like every other week, we've got something that's kind of special and diverse about the people who've contributed to computer science, and in this case, I wanted to showcase the contributions of immigrants. Only Stephen Cook won the Turing Award, but they both were really contributors to the fundamentals of theoretical computer science, and in this case, computational complexity theory. Now, we've heard a little bit about complexity in the class so far, talking about Big O, but we're going to talk soon about classes of problems that give us much more powerful theoretical tools for actually understanding the nature of the universe. And this is going to be captured in today's lecture through our discussion of the notion of NP-completeness and the Cook-Levin theorem, which is named after Leonid Levin and Stephen Cook. Now, both of them are still alive, so if you really enjoy today's lecture, you can shoot them an email, say, look, I heard about what you did, I think it's super cool, and maybe even meet them one day, though they are getting older. Now, taking us back a little bit, we're still in the middle of going through our different problem approaches. We talked about divide and conquer last week, and today we're going to start off talking a bit about physical simulation. So this is where we have a physical system that we're trying to predict, and we can encode the laws of physics within the computer system or within the program, or the laws of chemistry or rules in biology, and actually model what that behavior is going to be in order to develop a program which shows us how that system might behave in the real world. Now, depending on how sophisticated your modeling is, how many rules you choose to implement, you'll get a different level of detail in the predictive power of your program. So let's look at a couple examples here. So the first one I want us to think about is something that many of you might have seen if you are doing calculus this semester. How many of you have seen this kind of picture in your calculus class, either this semester or prior semester? Or in physics? Put your hand up if you've seen this picture in physics or something similar-ish. Or in high school? What we have here is a mass attached to a spring with a dampening, some item that's causing dampening. Our weight is going to have mass m. Our spring is going to have a constant that determines how springy it is, and our dampening factor is also our dampening element is also going to have a factor associated with it. Now, for today's purposes, you don't actually have to know how these interact. I'm going to just give you the physical laws that apply to this scenario. So, if anyone in the room remembers Newton's famous F equals ma law, force equals mass times acceleration, that's what we're drawing from here. What we're going to try and do here is calculate how far the spring will be at a given offset from our starting time. So if you remember Newton's law, the famous F equals ma, that is going to give us a way to relate the position of the spring to the time that has elapsed. Where A, that acceleration component, is going to be the way we relate it to time. So breaking it apart and putting in some of the physical laws we know around the way we know that springs work and dampening elements work, we get an equation that looks like this. Ma, which is just the F equals ma on one side, and then on the other side we have the forces. So we get negative CV, so negative the dampening factor C times the velocity of the spring, minus kx, where k is how springy the spring is, pulling the spring back to its original position, and x is the extension of the spring away from its resting place, where the spring is not extended at all. So you know if you leave a spring in its resting position, it doesn't pull any one way or the other, but as soon as you pull the spring out, it tries to go back to its original position. So our x here is going to measure how far away we are from that original position. Now what we can do is we can actually put in that time factor back into our equations, because we know that velocity is the change in distance over time and acceleration is the change in velocity over the change in time. Now really, if we were doing this in a very mathematically sophisticated way in a physics class, we might use calculus and use derivatives. But part of the power of using programming to solve a problem like this is, let's say you don't know how to do derivatives, or the derivative or integral of something is undefined. By modeling the behavior of the physical system at very small time steps and figuring out, okay, how much did the velocity change, how much did the position change, how much did the acceleration change, and doing it on small enough increments, you can actually approximate what the derivative or the integral would be very, very effectively. And of course, the smaller time step you do, generally the more accurate you can be. So let's actually go ahead and magic away the maths. And here we get, for small changes, so given our old acceleration, our new acceleration is going to be negative kx minus cv on m. Given our old position, our new position after some amount of time has elapsed is x, our old position, plus the change in time multiplied by our velocity. Our new velocity is going to be the old velocity plus the change in time multiplied by the new acceleration, and our change in time is going to be the old time plus whatever increment we're using to determine the time step that we should look at. So if we want to look at if we want to make our simulation really detailed, what we might do is pick a delta t, a change in time that's really small. On the other hand, if we want to do fewer iterations, if we say, okay, I don't care as much about the precision here, what I just want to do is do this in as few steps on the computer as possible, you might choose a larger delta t. Now, all of these you could easily write in a C program, and that's exactly what we're going to do, is set some number of iterations that we're going to run this through, or some new time t that we're going to want to reach. And then what we'll do is we will run this process over and over again, each time updating these variables until we get the values at the time that we actually want to know. And another thing that we could actually do with this is, rather than just running it forward until some final endpoint, we could actually graph our result. And that's what we're going to do here. So this is what we call a numeric solution to a differential equation. And a differential equation is just an equation that involves some elements of calculus, so derivatives or integrals. So just like we could write our physics equations in the form of derivatives or integrals, here we're just going to write out the numerical version, which is trying to do it by calculating what happens over repeated very small time steps. So at the top of our program, we're going to define our constant. Our constant k, which is called Hooke's constant in physics. Our c, which is the force of damping that's being applied. We'll get back to eps, which stands for epsilon, but is just a small number, and we'll talk about why we need that in a minute. And our interval, our delta t. So what is the frequency with which we're looking at snapshots of where the system is? We're also going to set a minimum and, this is a bug that has sat there for years. We're also going to set a minimum and maximum extension of the spring before the spring breaks. So if the spring gets more than 1.1 units away from its neutral position, it'll break in either direction. And then just a multiplier that we're going to use for our printing. Okay, let's skip first to our main function. So here we're going to set all the values that were in our equations before. We're going to set all the values that we need in our equations. A, V, X, T, M, delta T. And what we're going to take in as input is the starting position of the mass relative to its neutral position. So how far out do we pull the string? How far out do we pull the spring when we begin? How heavy is the mass? And then how large is our delta T? Then we're going to set the initial velocity and the initial time to 0. And then for each iteration of the loop, let's first look at what happens every time, ignoring the if condition and the termination condition. So we literally have just written out the equations that we saw in the slides a second ago. So if we go back, we can see that those exact equations are the ones that we've implemented here. Now let's look at our termination condition. So we have two interesting things here. We're taking the absolute value, the floating point absolute value of our x and our floating point absolute value for v, and comparing them to eps, which I said was a small number. So let's look carefully at our types. These are doubles. Now what do we remember about doubles? How many decimal places do they have? Do they have infinite decimal places? No. At some point, our doubles are going to run out of precision. And so what happens if our values for v or our values for x get too small is we're going to break the simulation, not because our equations are wrong, but because the numeric types that we're using are no longer able to represent the spring bouncing back and forth between such tiny increments, or are able to calculate our velocity with such small numbers. So at that point, essentially, we have to end the simulation and say, look, we're not going to be able to model that behavior below that threshold. And so that's why we terminate as soon as we are within some boundary of the stopping position. So if we're really, really, really close to if we're really, really close to the spring being still, then we're going to stop. Then what we have here is just something that says how often we output the graph of how far the spring is extended. So if t is bigger than the next output time, graph the current position against the current time, and then set the new output time. Okay, let's look at our graphing function. Our graphing function, again, is going to look at what is happening and display it. So the first thing here is if x is outside of the breaking point of the spring, so if it's larger, if it's more than 1.1 units extended in either direction, say that the spring fails and just end at that point. Then what we're going to do is calculate two scaling factors. You don't have to worry about the details there. And then we're going to print an axis, which by now should be familiar. If you go through this, you could figure out exactly what that looks like between drawing spaces and drawing bars to make the axes work. It's going to print x, which is the legend for the axis. And then it's going to print the extension of the spring. So let's run this. And the first argument is how far away it's extended. Now remember, the breaking point was 1.1 units away, so let's go roughly halfway. And let's set a mass of 1 and a delta t of 0.1 seconds. So if you look at what we get at the very start, the spring is extended, then it comes in a little bit, then it goes to the other side, then it comes in a bit more, kind of bounces back and forth. Now you'll notice that pretty soon it stops moving and we end. And we haven't really shown the spring's motion in great detail because our time interval was too large. So let's reduce our time interval by a factor of 10 and see what that picture that gives us. Okay, that didn't work. So maybe let's bring the spring out a little further and see what happens if we pull the spring out more. Now you can see the spring is starting from further out there, comes in a little, comes in, and then the mass of the spring and the dampening factor are causing it to stop moving. So let's try with a slightly less heavy spring. If the spring isn't as heavy, it kind of gets pulled in really, really strongly. What happens with a slightly heavier spring? With a heavier spring, with a heavier mass, I should say. With a heavier mass, what we're getting is a behavior where it goes back and forth a little bit more for longer. So now let's see what happens if I use a pretty heavy mass and pull it out 1.1. get some even more wild behavior. Now, what happens if I use a 10, massive 10? So you can just play around with this and see the different impacts of different size masses. You get these nice, pretty patterns. Now let's pull it out by 5. And then we finally get mechanical failure. We've pulled the spring out further than it should be. Our mass is too heavy. The spring breaks. And in many, many instances, you'll find that this is a very useful technique rather than trying to solve a very difficult set of equations. Doing a first check through this kind of simulation process can be very effective. And in fact, this is what those of you who go on in engineering degrees like mechanical engineering might actually end up using behind the scenes. So some of the more some of the more serious engineering programs are actually running these sorts of physical simulations behind the scenes, encoding a whole lot more physical laws to try and enable you to prototype things on the computer. And inside the computer, it's running all the same physical laws that would be happening out in the real world and allow you to tell if the thing that you're building would actually break. Would it push over? Would it shear? Would it bend? How would it behave? And of course, you can get arbitrarily detailed with your simulation. Now, beyond just physical simulations, this idea of solving fairly sophisticated equations that would otherwise require sophisticated techniques using a computational approximation works really well. So let's go to another kind of program, another kind of problem where we can use this idea of numerical approximation, which is another one of our programming techniques or our conceptual programming tools to solve a problem. So for those of you who have taken calculus, you'll know that you can approximate a differential equation or you can approximate a function using the derivative of the function. And that's essentially what we're going to do here to calculate cube roots. So here is our particular instantiation of the Newton-Raphson approximation method, which says if you have a guess x0 and you have a function f of x that you want to compute, you can make a better guess, which is x0 minus f of x divided by f dash x evaluated at that point. And the reason being is that the derivative tells you how much away from correct or from the direction that you're meant to be. The reason is that f of x gives you a gradient and gives you a direction that the function is going. And so using that idea of knowing where the function is going, you can scale that by where you are and figure out, okay, how far in the direction the function is going do I need to arrive at the correct answer? That's a very hand-wavy schematic way of thinking about it, but it might be enough to give you that intuition. So in the case of our cubed root function, we can calculate that as follows. So if we have an initial guess q, our new guess will be 2q plus x on q squared all divided by 3. Take that as q prime, which will be a better approximation, and then run this process over and over to generate q prime prime and q triple prime. We can also detect when our approximation method is kind of bottoming out by comparing our next guess with our previous guess and seeing, okay, do they differ by very much? And at some point you're like, okay, my next guess is very similar to my old guess. I'm not getting that much more benefit out of this method. And all we've done is encode this in C code. So we have next equals 2 times next, which was the prior guess, plus v on next by next on 3. So let's run that. So this is going to take in, where's the main function? Oh, there we are. There's our main function. So C root is going to take in a value that we want to calculate the cube root of, and then it is going to print out the original value, so x that we wanted the cube root of. the result of running the cube root function, and then to validate how good the approximation is, we're actually going to cube the cubed root to see if we get back the original value. Now, one thing you might ask is, well, how do we get our initial guess for what the cube root should be? Well, you can guess that the cube root is just the number itself. You don't even have to have a good guess for f of x. You could just guess x is what f of x, the result of f of x might be. And it doesn't matter if you're totally wrong, because this iterative process is going to enable your guess to get better and better over time. So your initial guess doesn't actually have to be that good. Of course, if your initial guess is good, that might require fewer iterations to converge on a good answer. This program is working through a fixed number of iterations. So we're going to repeat this process a given number of times and see how good our approximation can be. Our lines over here are to deal with the same issue that we had before with the precision of our floats or our doubles. So let's run cube root on 9. Let's run our cube root program on 9. Our approximation gets us 2.08. And if we cube that, it gets us back 9. Let's enter a value 81. And this gets us very close again to 127. You can see our approximations are really good to the extent that the error on these is not visible within the number of decimal places that we have chosen to print. Simulation can be used in really important settings. For example, when nuclear weapons were originally being designed, the way that the designs were being modeled was by using simulations. And in fact, that was the reason for the creation of some of the first computers, was to actually run these numerical simulations of different bomb designs and blast yields. And we'll do a quick aside here because I think it's kind of cool. A couple of weeks ago, there was a team of computer security researchers who'd found a computer virus that had been hidden up until a few weeks ago. And when they analyzed the virus, they found that what it did was insert very tiny errors in floating point calculations in the precision. Where was this used? This virus seems like it was used to infect computers in Iran, but where the Iranians were running nuclear weapon simulations. And this was done, I think, in the early 2000s. And so the simulations would all come out differently because of these tiny floating point errors that had been introduced. And whatever your politics around things are, this is a really interesting example of floating point numbers and errors creeping in and physical simulation all in one. So very interesting story that I'd encourage you to check out. So let's do one more example of this kind of numerical method. And this one is bisection.c. And the idea here is that we can also use what we know about the function in order to find roots of the function. So these are values, let's say you have a function f of x. These are places where where f of x is equal to 0. And so if we know which direction the function is trending, so if we know the function is getting smaller and smaller, and then at some point later it crosses the axis, and then we know that somewhere in the range between where it crosses, let me say that again. If a function is getting smaller and smaller, and then at some point later we find that it has crossed the axis, even if we don't know exactly where that 0 point is, what we can do is we can progressively halve our space to say, okay, at this point it was still positive and getting smaller, and at this point here it was negative and getting smaller. What if we go halfway in, and at each point we make a decision, have we gone too far? Have we gone far enough? Until we eventually find a really good approximation for the root. So let's look at the code for this one. So again, we're going to have this value epsilon, which is going to tell us, are we within such a small fraction of or within such a small value of the actual root that this is close enough for us, or do we want to keep going? And then we're also going to have a limit of the number of iterations, just in case we're actually not finding a root, because otherwise our program might run infinitely. So count the number of iterations, compute the function applied to our two values. So this is our value which we think is above the axis and our value which is below the axis. Calculate the midpoint of them, figure out the value at the midpoint between the two values, and figure out, is the root to the left of the middle or to the right of the middle? Do we need to make our next guess for x bigger or our next guess for x smaller? And then we just iterate on this. And it's a very, very simple function. And then what we're eventually going to do is calculate the midpoint of our interval. So if we are changing our interval each time, so it could be anywhere in this range, could be anywhere in this range, could be anywhere in this range, could be anywhere in this range. Because we're actually computing ranges and not the precise value, what we're going to do for the value of the root that we're going to guess at the very end is just calculate the midpoint of that range. And so that's why we're doing that divide by 2 at the end there. So let's compile that. So in this case, the function that we're going to run this over this weird complicated function for which finding the root might ordinarily be really annoying, and we're just going to find as good as we can get. And then what we're going to do is we're going to run it 3 different times with 3 different values of epsilon. So how precise do we want to try and be for the value of the root? Okay, so we're running at the same time, a few times, and each time we are getting the same value for x in the end. But what you'll notice is changing is the number of iterations that it took to find that root. So as we are increasing the precision, the number of iterations that it's going to take to converge will differ. So you guys remember the Monte Carlo Pi simulation from last time? I'm going to show you the code demo for that. So it turns out that actually doing the computation to generate random floating point numbers, but that are uniformly distributed in an interval in C is a little difficult. We are not going to step through the mathematics of that code and how to make it work. It is this annoying code, other than to note a couple things. So first, I am actually going to point out another type that we did use 2 weeks ago, but that we didn't really point out explicitly, and this is unsigned. And so unsigned is a modifier that we can apply to an existing type. So like unsigned int, unsigned char, unsigned float. And what this is going to do is it's going to say, remember how we had that complicated bit representation system where we were saving like 1 bit for the negative sign, or we were doing 2's complement, where we would effectively have one of the bits that was indicating whether we were in the negative half or the positive half. You guys remember that? What unsigned does is it says, actually, I want to use all 32 bits for the magnitude of the number. I don't want to split this up. And so you can assume that only positive numbers are going to be represented here. And so what this allows you to do is it often allows you to treat the bits more directly because you don't have to worry about that negative sign. So that's what we're doing here, is we're treating each byte just as it would raw appear in memory with not any signed interpretation of it. One other thing that I want to point out is what happens if you do not use srandom. So I'm going to write a very quick program. We'll do int main void rand I think might be in standard lib, and then we will call this. Might not actually work anymore, but we'll try it as a demo and see. what we're going to do is just generate 3 random numbers and then run our program 3 times. Oh, thanks. And we will do clang no random seed.c. That's the right syntax. There we go. And I should call that no random seed. 367, 367, 367, 367. The computer does not actually know how to generate random numbers. What's happening behind the scenes is that rand is a deterministic function, even though it sounds like random. What it produces is numbers that are actually pseudo-random. So if I go to my computer and say, hey, be random, how does the computer know what to do? Everything we've learned about thus far about computers is that they are deterministic, at least in a conventional sense. So how do you get your computer to produce random numbers? Well, one option is to say, well, we don't really need randomness. What is randomness in reality anyway? One interpretation of randomness means you can't predict what the next number will be. And so I couldn't predict that those numbers would be 367. And if I were to generate a 4th one, if I do Q, I don't know what Q is going to be. Does anyone know what Q is going to be? No. So let's compile that again. Clang, no random seed, show no random seed. Oop. I'm going a little too fast. I need another. There we go. 5, okay. Who knew that that would be 5? We didn't know. And so from one perspective, this is random because we don't know what it's going to do. But in another sense, it's not random because it's producing the same answer every time we ask for a random number. And so what's actually happening behind the scenes is in the C standard library, there's this rand function that is meant to produce a sequence of numbers that appear unrelated, but are still being generated by a deterministic process. So one thing you can do is you can say, okay, inside that function there are some variables, there's some state, the way the function's been set up, and I want to set up that variable such that it starts at a random point. So when it goes through the deterministic process next time, it looks different from every single time that we ran that deterministic process the last time. Now, one easy way of doing that, when you say, okay, but then how do we set the state to something different every time? You can actually use a function called srand, which sets the internal state. And what we're going to do is we're going to feed it the current time, because the current time is going to change every time you run the program. So if we set the internal variables of this random number generator using the current time, it's going to give us a different result every time. So now let's compile and run our program. So now that works fine, and now when I run the program, I get different answers every time. And one of my areas of early research when I started my PhD was actually on these random number generators. And my thought was that, well, if you are a spy agency and you can somehow figure out what time was actually used to start the computers, then you can guess what random numbers they would put out. And if you know what random numbers they're putting out, then you can use that to guess the secret values that they're using to protect all their communications. And so I actually showed in a number of instances how an intelligence agency like the NSA would be able to spy on people actually using the computers that are out there in the real world and using particular techniques to see some of the network traffic, figure out what time stuff was being generated, and then use that to figure out the secret information, and use that secret information to read everyone's communications. And so that was actually something that had quite a lot of impact in the real world, and I thought an interesting aside. And so if we go back to our Monte Carlo program, we're using a slightly different version of the rand function, which is a slightly more modern one, which is random, but we still need to do this seeding behavior. And then we're doing this fancy stuff to try and actually get a uniform distribution across a float. The reason we have to do this is because random produces integers, and remember that floats have this complicated structure with the mantissa and the characteristic, and so if we want to uniformly distribute our numbers within that range, we need to do some pretty clever trickery. And so you'll notice that I'm using -53 here because this is the number of bits in the mantissa in this particular instance. So I have to handle both parts of the number. So let's run Monte Carlo Pi. And if we leave this running for some more iterations, we should eventually get... It's almost there. We want one more correct decimal place. Okay, can we get another correct decimal place? It's struggling a little. So we got to 3 significant figures. Ah, we got it. So for the rest of the lecture, we're going to stand here watching Pi approximate. So let's switch gears a little and talk about some other programming paradigms. So this one is probably the biggest one from the last couple of years. I mean, underratedly, it was always sitting in the background, and this is optimization. And this is really the fundamental principle that underlies all of modern machine learning. So the core idea here, you have some function you want to compute or some output y, and you have some input x, but you don't necessarily know all the details of the function such that you can compute it directly. So for example, there exists a function that if I give you a set of English words, tells you the next most probable word across every word that humans have ever spoken. Now, of course, we don't have access to every word that humans have ever spoken, and we also don't know what that function looks like. Is it like x squared plus 3x plus 4x plus 5, where x is the first letter of the word, and then the resulting x is the first letter of the new word? It's probably not that function. But there is some function that you could write. It might be a really, really complicated function. The function might take up an encyclopedia worth of characters to write down. But there exists a function which, when you feed in a set of words, produces the next most probable word, given the distribution of everything that's been said by humanity so far. And in fact, we've gotten pretty good at creating that function. Even though we don't know the real one, we've got an approximation of that function, and that function is more or less the underlying function built into a large language model, which all of you were computing earlier in semester. So just like we were writing a program to do this computation that you were doing, one could also abstract that out and say, well, really what the program is doing is it's representing some kind of mathematical process, and we could write that out as a function. Because what we were doing was essentially, what we were doing in assignment 1 is I was giving you a large matrix, and you were computing just the output of that matrix given a particular input. Another way of saying what you were doing was just computing a function. Now, of course, figuring out what the values inside that matrix should be and how large the matrix should be and how to combine it is complicated, but this is one of the fundamental ideas of machine learning. So what we want to do is, given an input, produce a predicted output and try and make this better and better over time such that our predicted output gets closer and closer to the true output, the thing we really wanted. So if the thing we really wanted was the actual next most likely word, maybe we can get close and we can say, okay, well, the word that we're guessing is probably in the top 100 most likely words or something like that. And there are largely two forms of machine learning. There's supervised learning, which is if I give you a whole set of information that you can use to base your analysis off of. So in this example, it would be if I gave you a whole lot of books, you could guess what the next most likely word is using your prior examples of all the sentences that you've seen before in all of these books. But there is also unsupervised learning. And an example of this might be if I give you 100 newspaper stories, can you put the newspaper stories into 8 different piles of categories of what the newspaper story is about, but you're not allowed to substantively think about the meaning of them. You just have to use the distribution of the words. So for example, an algorithm that you might use is you might say if it contains the word foot or ball or run, then that is one category. And now that rule is going to be very coarse, and it's only going to produce one of the categories, but this is a fundamental task. Is I'm not saying I'm giving you a whole lot of data from you to learn about. I'm just giving you the specific things and arrange them in such a way as to learn something about them, and that's unsupervised learning. One of the most powerful techniques from machine learning is something we call gradient descent. And we've already seen some examples of this in some of the code we've already been using today, where we've been using the derivative to figure out in which direction the function is going. And again, this is one of the big ideas behind modern machine learning, is that we can use gradient descent to improve the quality of our guesses. So just like we were doing with the cubed root method, in machine learning, we can use, with the Newton-Raphson method, computing the derivative. In machine learning, we can use something similar. And the reason it's called gradient descent is as follows. Imagine you're at the top of a mountain, and you want to go to the valley. Now, you can imagine that your position on the mountain is represented by a vector which contains your coordinates. And what you want to know is, which way should I step next? Because you can't see the entire landscape. All you can see is where a tiny step would take you. And so you look in each direction and you compute the gradient or the derivative in those directions. Gradient is just another way of saying that. And you say, okay, this step takes me up a little in the x direction, down a little in the y direction, and in the z direction, it's the same. And then you look at the next potential direction you could go. Okay, this is down in the x direction and down in the y direction. And our goal here is to go down as much as possible to find the valley and get off the mountain. And so the rule is look at all the possible next steps you could take. In fact, make those steps infinitely small so that you're really like surveying the entire possible set. And we know how to do this using calculus. And then pick the direction that goes down the most. And one other way of reframing this is now imagine that our position on the mountain is represented by a function. And what the function is really doing is not mapping territory, but it's mapping the size of our error between where we are now and where we want to be. And so if you continuously go down the mountain, you're reducing your error as you go along. And so the goal here is to figure out which step, which change in your output will actually will actually ensure the greatest reduction in error. And now let's abstract this out one more time and say, okay, now let's imagine that the error is of something a little concrete. So we could say that our current position is our prediction of a house price, given its location, given how many bedrooms, and given how many stories the house is, or bedrooms and bathrooms, let's do. And those make up our vector of our position. And the output, instead of our height, is going to be the house price. And let's say now, additional to that, I've given you a whole bunch of historical house prices, including the house price for the particular house that you're looking at. And now what you want to do is look through each of the houses that have, and take out the details of the house. So the bedrooms, the bathrooms, and what did I say the last one was? Bedrooms, bathrooms, and location, that was it. So bedroom, bathroom, location, and for each house, compute the difference between the house price in the data set I gave you and the house price that you predicted. So that house price that you predicted is your height. Now sum those up together to get your total height across all the different house prices, and now change the function that you're using to predict the house prices such that that your function, whatever change you make, is in the direction that reduces that overall error, where the overall error is the summation of the error from all your different predictions of the houses. And that is really the key underlying idea of a lot of modern machine learning. It's come up with a function that computes, that is your prediction, have a data set that you can use to compare your prediction against that gives you the error, and figure out what tweak to the function what tiny tweak would result in the greatest difference between where you are now and where you want to be. So what tiny tweak will cause the error to go down the most, change your function that little bit, and then run this process again. Do all the predictions again, compare against your existing data set, and now tweak your function just a little bit so your error goes down just a bit more. Repeat this process often enough, and you can end up with a really good prediction. Now the details of well, how do you tweak the function? How do you compute the derivative on that function? What kinds of changes are we going to make? To understand that, you're going to have to take a class in machine learning. But I wanted to at least give you a little bit of the conceptual flavor of what that looks like. And now we have reached a wonderful place for a break before I take you into the final two components of our class for the semester. I will see you at 10:13. Okay, welcome back everyone. This material is some of the most exciting material, and one of the things that I really wish we taught a little more about, but that I'm going to give you a little flavor on. And these are some of the underlying ideas about what is actually possible for computers to do. Now, one of the core ideas underlying this is that when we think about computers from an algorithmic perspective, we have to develop what's called a model of computation. Now, you'll notice that this is one of the subjects that the university teaches is called models of computation. And the idea here is that depending on what your assumptions are about the structure, the underlying mathematical structure of the machine that you're using that's going to determine what kinds of algorithms it can compute. Now, for the most part, everyone is going to use a model called a Turing machine. And in fact, we can push that a little further to say a universal Turing machine. So all the computers that we use in everyday life are actually very close analogs to this notion of a universal Turing machine. That is our abstract mathematical notion of what a computer can do. That is our physical instantiation. Our actual computers in front of us can be captured really, really effectively by this mathematical model. No matter how you design this computer, no matter whether it is a calculator or a MacBook Pro, all of them can fundamentally do the same operations. Now, some of you might have heard of quantum computing. And this is an example of a model of computation, not just a physical device, but a model of computation that actually would run algorithms using different sorts of steps than the ones that are available to a classical computer. Now, we don't have time to explore all different models of computation, but one place that you've already had a little teaser of this is when we were doing analysis of algorithms. Sometimes we would say, well, this is the time complexity of the algorithm if we think about it very formally, but when we're using C, we've got all these weird kind of side things going on, like our floats we're using floats and they have limited precision, and numbers are addition and multiplication aren't actually constant time, and so when we compute this algorithm, the behavior looks a little bit different to our mathematical model. Now that's not to say that the mathematical model is wrong, or that we can't find a way to represent the way that C actually works, or that computers actually work in the abstract model. What it is more is it's showing the tension between these different kinds of models, and places where the mathematical formalism doesn't as cleanly map to the physical machines that we have. So out of staying within the world of classical computing, we largely have two different kinds of models that we're going to look at, although there are a large variety of them. For our class, we can think of deterministic and non-deterministic. So non-deterministic is where you allow randomness to be present in one way or another. And as we've seen, a lot of the times the randomness is only pseudo-randomness, but that's going to be good enough for our purposes. So let's make this all a little more concrete. Let's go back to our Sudoku. Remember, we had our puzzle over here, and here is just a sample. And here is just a sample puzzle. Now we could write that out using the logical formalism that we had constructed before. So let's look at our starting assignment. S111 is false, it's set to 0. There's nothing in square, there is no 1 in square 11. 112 is also 0. There is no 2 in square 11. Same for 113, 114, 115, 116, 117, 118. But 119 is set to 1. It is true that square 11 is set to 9. And we can do this for every square, write out the statements that are true. Now we've done this before. You remember seeing these complicated clauses that capture all the different constraints on the Sudoku. And we can write these out. And we talked about it last week as a form of constraint programming. Now we can also start to analyze this and say not only how do we solve the problem, but what is the running time of the problem? Going back to our exercises, particularly the work that Hanju did so nicely with you earlier in semester around trying to figure out how we can compute computational complexity for a given problem, for a given piece of code. So we also had So let me reframe the problem a little bit, and rather than just saying, what is the solution to the Sudoku, we can construct a version of it that's called a decision problem. So is this a Sudoku that has a valid solution? That is the function we want to compute. Not what is the solution, but does there exist a solution? This is very similar to when we were talking about subset sum just a week ago. So is there at least one combination of settings for all the variables with x, y, and z all between 1 and 9, so any square can be set to a value between 1 and 9, and the ranges of the squares are between 1 and 9 and on two axes, so our x and y axis, such that all the different clauses that we've come up with can be satisfied. That is, we don't want it to be the case that for any of the restrictions that were put on a valid Sudoku, we don't want any of the restrictions to be violated. And so another way of saying that is we want all the clauses to be satisfied. And we can call this SAT for short. And this is in fact a very famous class of problem. Now there is this lovely paper which we talked about called Showing Sudoku as a SAT Problem. But if I give you the values of s, x, y, z, how long until you know if the solution is valid? So this is not me asking, is there a valid one? It's asking, here are all the clauses, here is my guess for a valid Sudoku. What is the big O time of checking if the solution that I give you satisfies all the clauses as a function of the length of the string that encodes all of this? So let's say the string is, like if it's S110, if it's S111 equals 1, S123 equals 1, and then I give you all the clauses and we just put that into a long string. If that string is of length n, what is the big O running time of a program that checks if all the clauses are satisfied? And We'll give that a round for a guess. Remind me your name again. It's been a little while. Thomas, what do you think? The question is, let's say I have given you the solution to the Sudoku in the form of a string that says S11 equals 1, S22 equals 7. Yeah, a full complete solution. And I give you the list of clauses that it has to abide by. And this is all in a super long string of length n. What is the runtime of the program that checks if the solution satisfies the clauses?
Polynomial.
Polynomial, that's true, so it's some polynomial.
Runtime.
Yeah, runtime.
Constant. No, wait.
So the string is of size n, so we want it parameterized in n.
Maybe O of n.
So for each clause,
How many clauses?
the string is of length n. So we're, instead of thinking about the number of clauses, we want to think about the size of all the clauses, because one clause might be big.
I don't know.
So each clause, how many times will we need to check it? So thinking, were you here in the prior Sudoku lecture?
Nothing.
Ah, okay, so it's a little trickier. Might have been last week.
How many times do you check, like, 81 times? Or how many times do you check each clause?
Well, it turns out that what we can actually do is we can boil down the clauses to the point where we can actually compute if this is a valid solution in O of n time. And that's one of the really nice things about satisfiability is once you have a valid solution, it's actually pretty simple to check. Because you go through each clause and you check, is this clause satisfied? You look at the setting of your variables, and you can very quickly check, yes, this clause is satisfied, no, this clause isn't satisfied.
Constant.
It's not constant time, it's linear time.
I'm about checking the clause.
Oh, checking the clause, no, checking the overall solution
Is O of n.
is O of n. Okay, so keep the microphone. You can turn it on mute for the time being. And what we have is this kind of behavior. To check if a solution is a valid solution is only going to take us O of n time. Now, I'm not sure we talked about this in great depth earlier, but what O of n is O of n as a mathematical object is really a set. It's a set of all the possible functions in the world, every single function. So imagine all the functions, like 2n, 3n, 3n plus 4, 6n plus 5. They're all different functions, and all of those functions belong in the set O of n, because all of those functions have the behavior of an O of n function. And so that's how we'd really write it in a little more mathematical precision. And so our function, that is O of n, also belongs to the function, to the complexity class O of n to the k. Because O of n to the k are functions that behave much, much bigger and take much longer to run. And so linear functions are within that because they're fast. And so anything faster than O of n to the k is within that big O of n to the k set. And so we're going to call this polynomial time, as Thomas actually just kind of jumped the gun on a little. So what we can say is that sat can be checked in polynomial time, because the function that, the running time of a function that checks whether a solution is valid runs in O of n time, and O of n time, any function that runs in O of n time can also run in O of n to the k time, because O of n to the k is the bigger set. It contains things that are more complicated and take more time to run. And so we're going to use this, you're going to hear this throughout computer science over and over again, polynomial time. That means no matter what polynomial you write, the thing that you care about runs within big O of that polynomial. That's probably a little imprecise to say it that way because all polynomials are kind of that same complexity class. But our general idea is that if you have a function that you say runs in polynomial time, that means it sits in this set big O of n to the k. Kind of get what I'm saying there? Or is someone confused and wants me to explain it a little again? Think we're good? Okay. So any problem that is O of n is also O of n to the k. So this is where we're about to get a little more complicated. So what we're going to do is distinguish between the amount of time it takes to check a problem and the amount of time it takes to generate that solution that we can later check. So if there exists an algorithm that checks the solution to that problem in polynomial time, we're going to say it belongs to a class of problems called NP, which is all the problems in the world for which there exists an algorithm that checks the validity of the solution and where that can run in polynomial time. Okay, so NP is going to be the class of all problems that can be checked in polynomial time. Now there are a few ways of defining it which add some subtlety here. The reason for the n we're not going to go into, but at least heuristically you can think of it this way. So this is our next trick, is we're going to talk about this idea of reductions. So a reduction is if I give you a specific version of the problem or a specific instance. So I give you a Sudoku with some squares filled out. For any Sudoku, is there always a way to write it as a set, as one of these satisfiability problems? The answer is obviously yes. That's what we spent like 10 minutes doing before and like 30 minutes doing last week. So what we can say is that Sudoku reduces to SAT, because any Sudoku puzzle that you give me, I can always write it as a copy of this other problem that we call SAT. So that's a reduction. And what this means is if we have a way to solve SAT, generally, if there's an algorithm, if you give me a program that can solve SAT, then I can also solve all of Sudokus. Because step one is convert the Sudoku into a SAT, use the program I just gave you that can solve any SAT, and then convert it back to a Sudoku, and there's your solution. So that seems fairly straightforward. If I give you a magic box that can solve problem B, and I tell you that anytime you have problem A, there's a way to convert it into problem B. So you convert A into problem B, you run the magic box to solve problem B, and then you convert problem B back to problem A. And so that is called a reduction. So this means if we can decide all SAT problems in polynomial time, so if we can decide if there exists a set of variable assignments that correctly solve a SAT problem, that satisfy a SAT problem in polynomial time, then we could definitely decide whether a Sudoku has a valid solution, a given Sudoku, in polynomial time. And this turns out to be the same for solving, although we'd have to design our mathematical formalism a little bit differently. So not just the decision version of the problem, but the version where I actually ask you to produce the solution. So there are differences, and those differences are going to be really important when it comes to constructing some of the proofs. But for the moment, you can kind of blur them in your head because this is a first year class. So practically, this might seem weird to you because you guys solve Sudokus all the time, and you can also practically solve a whole bunch of SAT problems all the time. But what's important to note here is that this is not a comment about the particular instance of a Sudoku that you're solving, or the particular instance of a SAT that you're solving. So as an exercise, Tom's going to help me. If I give you the following satisfiability problem, it's a two-variable satisfiability problem, and the constraint that I'm giving you, so we've got x and y, and the clause that you have to satisfy is either x or y. What is a valid solution to that satisfiability problem? Yeah, so x and y can both be true or false, and the clause that you have to satisfy is x or y.
True, true.
True, true. What's another example of?
True, false, and false, true.
Yep, true. So there are a whole bunch of easy ways to solve that particular instance of a satisfiability problem. So the question is not, can you find an easy one of these problems? The question is there an algorithm that no matter which satisfiability problem I give you, no matter which clauses and how many variables, you can still solve it in a given, let's say, polynomial time? Is there such an algorithm that works for any SAT problem I give you? Is there? Well, we don't know one, but we're going to talk a lot more about this in a couple minutes. So another kind of way of thinking about Sudoku specifically, just because we've been harping on a bit about it, is Sudoku is a specialized variant of what we'd call a Latin square problem. And a Latin square problem is this general idea of you have a big grid, you have to fill it with numbers, there are some constraints. Sudoku has a very particular set of constraints and a particular grid size, but you can generalize this to the more general version of Latin squares, and then we can show that Latin squares reduces to SAT. So just like Sudoku resolved to SAT, the more general class of Sudoku-ish like problems also resolves to SAT. Now, one other just note that I want to put here is that for any version of SAT that we have, we can easily find a way to break it up so that instead of like S111, S112, S113, S114, S115, and, we can always break it up into a maximum of 3 clauses at once just by arranging our ands and ors specifically. And you can kind of do this exercise for yourself and show that for any instance of SAT, you can reduce it to 3 SAT. So if I give you a whole set of clauses that are as long as you like, you can break it up into a way such that there are only 3 variables at a time that you're ORing together. And you can just write it that way. And we're going to call this 3SAT. And the reason why we're going to do this is because 3SAT is what's used in the literature, and it turns out to be used very effective for proofs. So I spent a lot of time talking about Sudoku, a lot of time talking about SAT. Let's talk about some other problems. So does everyone have something that they can like sketch out in front of them? Or on your laptop? Or in your head? Or on your phone? Okay, so here is a map of Australia. Can you color the states with 2 colors such that no states with the same color touch? What? Come on, I'm giving you I'll give you 15 minutes. Who said no? Okay, let's give you a microphone. Tom, your time's up. Sorry. Remind me your name again?
Jay.
Jay, that's right. Okay, why not?
There's a point where 3 states border each other. So no, if it's only 2 colors, then 2 states have to touch with the same color.
Oh, darn. I thought I'd come up with a great in-class exercise. That's so annoying. I blame past Shannon. So yes, Jay is totally right. There is no way of 2-coloring a map of Australia, which is how we call this. The general problem where I give you a map and I say, can you color in the map with 2 different colors such that at no point do 2 different nodes on the map have the same color if they're adjacent to each other? That's called 2-coloring. And so in this case, it's obviously impossible because we have 3 in that instance. We have more than 2 states adjoining each other, so there's no possible way of doing it. What about 3-coloring? Okay, I'll give you a minute. Can you 3-color the map of Australia? Jay? Can you 3-color this map of Australia? What do you mean? Can you do it?
Since the middle state was the only one that we couldn't color with just 2 colors, if we make that the 3rd color, yeah, then we can.
Okay, so now we've got a valid 3-coloring for our map. So first question for you, is this problem in NP? Does there exist an algorithm that no matter what map and solution I give you, you can check if the solution is valid in polynomial time? Okay, what is the algorithm?
You check that.
You use the microphone.
To check that each, so just to check that it's a valid solution.
Yeah.
You would just have to check that each state is not the same color as the states that borders.
So let's put it in slightly more computer science-ish language. So for each state,
check the states next to it.
Adjacent. Yeah.
And check that that state does not equal the color of the state.
Okay, that sounds pretty good to me. So let's go ahead and do that. Except I'm going to draw a new map of Australia. So how many of you have drawn a map of Australia before somewhere? Like you've done the, maybe the little thing with your hand or drawn a piece of paper. This is people thought I was an excellent artist as a child. And so this is my drawing of the map of Australia. And you can see, so where's Tasmania? There's Tasmania in the corner over there. We have Victoria, New South Wales. What is that green blob over there? That's South Australia. What do you think? 10 out of 10 artistic abilities? And so this is my graph representation drawing of Australia, which turns out to be actually a really nice way of representing this three coloring problem. And this is in fact the traditional way of talking about three coloring is as graph three coloring, because you can represent any map as a graph where adjacency is represented by an edge and where each individual region on the map is represented by a node. And so this allows us to formulate the checking algorithm really simply, which is check it by examining each vertex's neighbors. Okay, so what is the big O runtime of the algorithm you proposed? So let's say we have, let's say that we are bounding the number of edges by n and the number of nodes by n, just to make life simpler. So instead of v and e, we're using n and n.
You would have to check each node, at least.
And how many edges can each node have at maximum?
You can have n? No, yeah, it could have.
Yep.
So you'd have, it would be n squared.
Yeah, so n squared is a really large upper bound. Obviously, we don't need to do that necessarily because if a node has more than 3 neighbors, then there is no way to 3 color it because you'd need another color. So the really super rough one, if you're just like, okay, I don't care, I just want to know if it's polynomial time or not, you can instantly say it's polynomial time, or you could even go a little better, well, significantly better than polynomial time. But either way, we don't care. We just want to know if it's in the complexity class NP. So now, here is the trick. We are going to turn our graph coloring problem into a SAT problem. Remember this notion of a reduction? So I'm going to hopefully show you that for any graph 3 coloring problem, we can represent it as a SAT problem. This means that if I had a magic box that could solve SAT problems, if I can do this successfully, if I have a magic SAT box, then I can also solve every one of these graph 3 coloring problems. And so what this means is that SAT must be at least as hard as graph 3 coloring. Okay, so let's turn it into a SAT problem. So let's create our variables. And so in this case, we've got 7 different regions of Australia. And so I is going to range between 0 and 7. So that's just going to indicate the variable for which state we're talking about. And then C is going to be the color, either 0, 1, or 2, that represents our 3 different color combinations. So for example, if Tasmania is state 0 and we're coloring it purple, and purple is color 2, then S02, if that is part of our solution, would be set to true. So let's do the same thing we did with the Sudoku and write out our clauses that constrain what a valid solution looks like. So for node 0, which I think is Western Australia, every node must be at least 1 color, so let's write out a clause that ensures this. So it is either the case that 0, 0 is true, 0, 1 is true, or 0, 2 is true, because for node 0, which is Western Australia, it must be one of the 3 colors. So at least one of the 3 color variables for Western Australia must be set to true. Then we have this slightly more complicated looking clause, which is node 0 can't conflict in its color with its connected nodes. So they can't have the same, it can't be the same color as either its connected one. So let's break this down a little bit more. Okay, so let's say it is the case that S00 is true. If S00 is true, then it must also be the case that it is not true that S10 is true and S20 is true. Now let me phrase that another way. S00 means Western Australia is orange. If Western Australia is orange, it must also be the case that not Northern Territory is orange and not South Australia is orange. And that's what we're saying in that clause there. Now, it's also possible that we live in a world where we haven't colored Western Australia orange. And so that's our second clause, our second big clause over there. This is the clause where instead of coloring it orange, we've colored it purple. So we might live in a world where we've colored it orange. If it is orange, then that second little subclause with the two knots must be true. Or we could live in a world where we have instead colored it purple. And if we have colored it purple, then its two neighbors can't also be colored purple. Or we could be living in a world where we have colored it green. And if we have colored it green, then its two neighbors can't be colored green. Now, of course, I've only written out the clauses for this one node of the graph. But we could write out all the clauses for everything, and we can write out our variables, which are just SIC, where I ranges between 0 and 7, and C ranges between 0 and 2. And then we've converted our graph 3 coloring problem into a SAT problem. So if we can decide if there exists a valid solution for any SAT problem, then we could also decide if there's a solution for any graph coloring problem, if we have an algorithm that can do this for SAT. Because anytime we get a graph problem, a graph 3 coloring problem, all we'd do is convert it into SAT, use the magic SAT algorithm, and then would solve the graph coloring problem. Graph coloring cannot be harder than SAT. Why? Because if SAT is a little bit easier, what we could do, if SAT is easy, what we can always do is we can convert our graph problem to the SAT problem and then just use the SAT method. So either we're in a world where there is an easy method for solving graph problems that can't be used to solve the SAT problems, and if we're in that world where we wouldn't bother doing the conversion, or we live in a world where the best way we know to solve graph 3 coloring is to do that conversion process first. And so in either case, we know that SAT must be that graph coloring can only be as hard as SAT in the worst case. Okay. So we're going to take another step forward down this path. So now let's define a class of problems, and we're going to call this class of problems NP-hard. And this is going to be the class of all problems that are at least as hard as SAT. What we're going to do is we're going to later understand this class NP-hard as really all problems that are as hard as the hardest problems that can be checked really efficiently. So remember, NP is the set of all problems that can be checked fairly easily. So we've already talked about our notion of reduction, we've talked about Sudoku as graph coloring. So we've got one more proof that we're going to do, which is that subset sum, which we talked about last week, is NP-complete. And what NP-complete is going to be, it's going to be this extra class of a problem that is both checkable quickly, but is also really hard. NP-complete that we're about to talk about now is a problem that is both really hard to solve, as hard as the hardest problems in NP, but also it is in NP itself. So there is a difference between being as hard as the problems in NP and also being in NP yourself. You can be a hard problem, but also have it be hard to check a solution. So a problem is NP-complete if it's easy to check, so it's in NP, but is also NP-hard. And what we're going to do is we're going to show that subset sum is NP-complete. So is subset sum in NP, is it easy and quick to check if you have a valid solution to subset sum? Now subset sum is the problem where if I give you a backpack that can have at most 100 kilos, and I give you a whole bunch of items, and I ask you, find me a collection of the items that weigh up exactly 100 kilos such that you've precisely packed the backpack. Now, asking you, is it in NP is saying, if I tell you which items they are, and I tell you what their weights are, can you tell if it is, if it sums to the correct value? Okay, what's the algorithm?
Add up all the sums, the weights.
Okay, now imagine that I've given you an array that contains all the items. Can you still do it? Okay, how would you do it? If I've given you the indices of the arrays of given you the indices in the array of the items that we're including.
just add up all of the masses of the items at those.
Yeah, same solution as before. So we can write it out a little more formally, but it's probably not necessary. You can get it intuitively. So if I give you a set of indices that tell you which items in the array to include, you go through those indices, you sum them up, and if it does indeed equal the maximum weight that you're allowed, then your solution is valid. You've done great. So if we compute the big O time of this, we'll get a maximum of n times the magnitude of x, where x is the size of the number. Now the reason is because, remember, we talked a little bit that addition isn't always actually constant time, and one of the things that we have to be really careful about here when we're talking about problems that are close to SAT, remember we were talking about SAT in terms of the length of the string of the clauses. So if we're thinking about numbers that might also be really large, we also have to actually think about the number of digits in this case. In the world where you include every item to get up to it, that would be O of n, because you have to add n items together. It's not as easy as just saying it's O of n, because those numbers might be large numbers, and in this world, we're not treating addition as constant time, because we're not, for SAT, we're dealing with potentially large strings. So we include this extra fudge factor, but it's still pretty clear to us that it's still polynomial time. So we can check a solution in O of n to the k. So subset sum is in NP. So now we go back to our NP hardness, and for subset sum to be NP complete, we need it to both be in NP and also be at least as hard as SAT. Now, this is a little tricky because what we've done so far is kind of a reduction the other way. We've shown that we can turn graph coloring into SAT, which means that graph coloring can't be harder than SAT, but it could be easier. And so what we could kind of do is the reverse. If we can convert SAT into subset sum, then we can show that subset sum, that SAT is at least easier than subset sum is. And so this is a different kind of reduction than the two we've just done. Okay, another way of saying this is if we can show that we can solve every 3-SAT problem by converting it to subset sum, and then we use our magic subset sum solving box, that means that it must be the case that 3-SAT is no harder than subset sum, because either there exists a really efficient algorithm for 3-SAT, in which case we don't bother with the conversion, or we live in a world in which the best algorithm is the conversion, in which case what we do is we convert it, we use our magic box to solve 3-SAT, we convert it to subset sum, we use our magic subset sum box, and then when we get the result, we convert it back to SAT. So now we're doing a reduction in the other direction. And I will actually say that I get confused all the time, particularly when standing in front of you, about the direction of reductions. Like, wait, does this mean which problem is the harder one if I'm reducing this to that? That is, if you ever take like a very advanced algorithms class that does this stuff, that is one of like the really big traps that's easy to get confused about. I haven't done a very good job of memorizing it, but I think that's the actual way to do it. You can logic through it every time, but it takes a while. Okay, so now let's do this reduction. And this is kind of cool because the reduction is a little weird and funky. So let's do our reduction, and given a 3-SAT problem, let's convert it into subset sum. And so this is the trick, and you're not expected to be able to come up with this trick by yourself. This is like a really exciting result at the time. In an advanced algorithms class, one of the things they teach you is a whole bunch of patterns for the reductions you can use, but coming up with like the first reduction of each type is really like a big research problem. Okay, so let's imagine we have this example 3-SAT problem, and we're using this as an example to show that even though we're only doing the reduction on this particular example, the process is repeatable. So let's say we have our 3 constraints, C1, C2, and C3. We have 3 variables, x, y, and z, because 3-SAT is the rule that unlike a normal SAT, we're only going to deal with 3 different variables at once. And so our constraint 1 is it must be the case that x is not true, or y is true, or z is true. Constraint 2 is that either x is true, or not y is true, or z is true. And constraint 3 is not x is true, or not y is true, or z is true. And what we want to know is is there a solution to this problem that satisfies all the constraints? Is there a setting of x, y, and z such that all three of these constraints end up being satisfied? And so we write out this weird table. This is how we do the reduction. And so in C2, x appears. So on our line for x, we put a 1 in the C2 columns. So if you look at C2 over there, you can see that x appears. So in C2's column next to x, we put a 1. There is also a 1 where x and x are. The reason we put a 1 there in the x column is because we want it to be the case that only one of x and not x can be true. And so at the very bottom in our total row, we're going to put a 1. And our goal here is going to be to select rows that add up to produce this number at the bottom. And so if we would select both the number that has a 1 in the first column for x and it has a 1 for the not x, then adding those together will not produce the 1 at the bottom, because 1 and 1 equals 2, and there's no combination of x and not x, that 1 in the first column and that 1 in the first column first row and that 1 in the first column second row, that you can add together and still get a 1. If you add 1 and 1, it's always going to be larger than 1. And so we ensure that they conflict, and the way we ensure that they conflict is by putting a 1 in both of those positions. Likewise, for y and not y, we set up a column so that y and not y cannot both be selected at the same time. And the way we do that is we say if you choose the row that has the y in it and you choose the row that has the not y in it, there is no way to sum them together to get their column to add together correctly, because 1 and 1 still equal 2. And the same for the z column. And then what we do is we also have these columns for each of our c's. And because our c's are more complicated, what we're doing there is saying which variables have to appear in them. So for example, C2, if we look column-wise, has an x in it, it has a not y in it, and it has a z in it. And so in those respective entries, we've put them there. What we want to do is we want to ensure that from each of the clauses, we get at least one of those values being true, because they're ors, right? Or this, or this, or this. And so at least one of those rows in our big tableau thing here has got to contribute a 1. Because if we don't select a 1, then that means that clause isn't satisfied. However, it's also possible that two of the individual elements of a given clause are satisfied. So we could have, let's imagine we're just looking at C1. It could be the case that not x is true, and y is true, and z is true. If that were the case, then we'd actually get a contribution of 1 and 1 and 1, and then we'd get to 3. And so the way we solve this is by having the full column add up to 4, and then we allow ourselves to say, okay, maybe we live in a world where only one of the individual bits is satisfied. If we live in that bit, then what we'll have to do is select this W rows at the bottom. The reason we have these W rows now is to allow for the possibility that it might be one of the things that's correct, or two of the things that are correct, or three of the things that have been added up. And then we can add whichever W row we like in order to account for those different worlds. And so our goal here is now essentially subset sum. It's choose all of these items where each item is a row, choose as many of the items as you like so that you get this exact value at the bottom. So don't worry if you haven't followed this proof, it's actually a little tricky. But let's take each of these rows and imagine that they are the items that we need to put in our backpack. So choose one of either x or not x. At least one of these has to be true. And so the row for x had 1, 0, 0, 0, 1, 0, where that first one was to ensure that it conflicted with not x. And that other one was to ensure that it appeared in the clause in which it appeared. And likewise with not x. So choose one of x or not x, choose one of y or not y, choose one of z or not z, And then you can finish with a selection of these additional weight ones, which say, okay, for clause 1, we might be in the case where one of them was true, or 2 of them was true, or all 3 was true. And then what you want to do is check, have the ones you've selected enabled you to get to that target number? And now why does this work? Let's take one more look. Okay, so let's imagine we pick both x and not x. There is no combination of the other things that we could pick that would still allow a 1 in that first position in the target string. And so what we've really cleverly done is for each of the digits in that target weight that we want to get to, we've ensured that we've set up our items that match the clauses such that by choosing the item, you've effectively set which of the variables you believe to be true or not. What we've shown now is that 3-sat, we could be living in 2 worlds. We could be living in a world where 3-sat is easy because we have a special 3-sat algorithm, or we could be living in a world where the best way to solve 3-sat is to convert it into subset sum. But we already kind of know that 3-sat is hard. I mean, we haven't really proven it yet, but we've converted all these other problems that seem difficult to it. And now we've said, well, subset sum is even more difficult in a way. And we could also even do a reverse reduction. We could then say, well, what about if we can convert every subset sum to every 3-sat? And if we can do that, we can show that they're equivalently as hard as each other. And this idea of reducing problems to each other eventually produces a figure that looks kind of like this. There are all these different problems in the world, and some of them we believe to be hard. And by doing reductions, we can say, well, this problem is at least as hard as this, at least as hard as this. And eventually what we find is that satisfiability, SAT, turns out to be a problem that pretty much all of the other hard problems can reduce to, and we then can also do these reverse reductions, which allow us to show that this whole class of problems is really as difficult as each other. So if we can solve subset sum, then we can solve 3-sat, and if we can solve 3-sat, then we can solve subset sum. And I'll leave you to figure out how we do the easier reduction from subset sum to 3-sat on your own. It is doable. It takes a bit of thinking, but it is doable probably at your level. So if you can solve the hardest of all of these problems in polynomial time, then you can solve them all. Problems that you can decide if there is a valid solution in polynomial time, we're going to call P. And so these are problems which are solvable in polynomial time. Now we don't know, does there exist an algorithm to solve 3-sat in polynomial time? Does there exist an algorithm to solve subset sum in polynomial time, or even decide if there's a valid solution? If there does exist such an algorithm, then they belong to the class P. Otherwise, question mark. Now, this takes us to probably one of the highlights of all of computer science in the last 100 years, and this is the Cook-Levin theorem. And the basic idea here is to say if SAT is solvable in polynomial time, then all problems in NP can be solved in polynomial time. Every single problem that is checkable quickly can also be solved quickly. And this is really amazing because it collapses all these problems down together. And we call this NP-completeness. And this won Cook the Turing Award, and is really one of the major, most important results in theoretical computer science in the last 100 years. Really quite beautiful, because it kind of wraps up all of this stuff that we've been thinking about together from the entire semester. So let's draw the picture to make this a little clearer. So we have all the problems that we can check if a solution is valid quickly. That's our NP circle here. Then we have all our problems that are really hard. That is NP hard. Those are all the problems that are at least as hard as SAT. They could be harder, but they're at least as hard as SAT. And then there are problems like SAT, which we can check a solution quickly, but we believe the problem is still really hard. And so they end up in this middle area here called the NP-complete area, the set of all problems that are checkable quickly, but that might be hard to solve. But we haven't actually answered this question. Is SAT solvable in polynomial time? I said, it might be. This is what happens if it does. But is SAT solvable in polynomial time? Does anyone know? The answer is no one knows. This is one of the Millennium problems, which is probably the most famous, most prestigious mathematical problems out there. Each of them have a $1 million prize attached, and many of them are considered to actually be unsolvable. It's believed that humanity will never have an answer to many of these questions. And the question phrased another way is, which of these two worlds are we living in? Are we living in a world where there does exist a polynomial solution to SAT, in which case P equals NP? Any problem that is checkable in polynomial time also is solvable in polynomial time, because we already know that the problem is in NP when we start out, and then if the problem is in NP and SAT has a really efficient polynomial solution to it, then we could always just convert that other solution to SAT. So if SAT is solvable in polynomial time, then that little area NP-completeness disappears, because we can always just use our SAT magic box. So that's that world over here. On the other hand, if there does not exist an algorithm anywhere that could be found, there is no such algorithm, then we live in this world here, where P does not equal NP. So there is a $1 million USD prize for answering the question. There are lots of reasons to think that we're unlikely to make progress on here, and this is one of the really foundational problems. This does not mean you should never think about it, but probably not worth staking your career on. And there's this fun page of all the people who have claimed that they have a solution to it, but don't really. And if you watch Archive, which is where people post a lot of mathematical papers, you'll see crazy things coming out around this. But why do we care about NP? Are there actually real problems that we care about that are NP hard? So here are some real world problems that are in NP and that are believed to be hard. So for example, if I have a certain theorem that I want to prove, a mathematical theorem that I don't know if it's true or not, can you have a computer automatically decide whether the theorem is true or not? So automatic theorem proving is one of these. If you have a network of cables, let's say you're in Australia and you have telephone poles everywhere and you want to figure out what is the best way of running cables between them, that's an NP hard problem. What about if you want to figure out how to put things on a circuit, such as you want to minimize electrical interference and optimize that? Also NP hard. What about scheduling things perfectly? NP hard. Best way to pack a backpack? NP hard. Best way to pick up passengers? NP hard. How to steal Bitcoin. Now this one is interesting because it's probably not NP hard. It might actually be in an intermediate class, but it's still checkable. It's still an NP. So we know that if you can crack the algorithm that is used to secure Bitcoin, then you can check it really efficiently, because you can just run it on the computer and check if you can steal the Bitcoin, and that's efficiently doable. We don't know if there is an efficient algorithm to do it in polynomial, to solve the problem in polynomial time. So all of this talk is in one way a little silly, because in practice we do all of these things. I showed you a whole bunch of those problems and you're like, well, wait a minute, Telstra does build telephone poles in Australia. They're not worrying about the fact that maybe it's an NP-complete problem. So this notion of hardness is really referring to the entire type of problem. So it's saying that for any instance I give you, your algorithm should still work. But in practice, we can use things like approximation algorithms to get close enough to, or good enough to an answer, or sometimes even get the optimal answer for specific problem instances. But what would it mean for the universe if P equaled NP? Now, probably my favorite theoretician, and he's a wonderful and kind person as well, is a guy named Scott Aaronson. And we've already seen him in this class once before when we were talking about time travel and complexity and infinity. But he wrote this wonderful paper called NP-Complete Problems and Physical Reality, which I actually, this one I legitimately recommend all of you reading. It's fun. It's a super fun paper to read. And he's got this sentence in it, which says, if P equals NP, the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once the problem is solved. So maybe we should actually be grateful that these hard problems exist, because they're what, in one way, allows us to truly be human. And that's my little I mean that seriously. This is my like little philosophical moment again. This is our second philosophical moment of the semester, I think. So, got 45 minutes. Is this the end? No, let's do a little more. Okay. So I want to take us back to the Fibonacci problem and wrap up all the themes of the class with the problem of how to communicate the nth number in the Fibonacci sequence. So at this point, you've seen it all before, but let's zip through it a little bit, and then we'll get to our our final surprise.
The human X chromosome contains hundreds of genes associated with a wide range of diseases, including hemophilia and red-green color blindness. An interesting aspect of the X chromosome is its inheritance pattern. Unlike the Y chromosome, where the number of possible ancestors must be equal to the number of generations, or the 22 other autosomes, where the maximum number of possible ancestors is equal to 2 to the power of the number of generations, X chromosome inheritance is a little more complicated. A male will inherit one of 2 possible X chromosomes from his mother, either from his maternal grandmother or his maternal grandfather. A female will also inherit one X chromosome from her father, introducing an asymmetry in the number of possible ancestors. Turns out there's an efficient way to calculate the number of possible X chromosome ancestors using the Fibonacci sequence. For a male, the number of possible ancestors is equal to the nth Fibonacci number, where n is equal to the number of generations going back. For females, this method can also be used, but n is equal to the number of generations plus 1.
And a very big thank you to Dr. Ellister for that. Hopefully I will see him for lunch later today. Okay, so why do we care about the Fibonacci sequence thing? Well, one reason is that it appears in a whole bunch of places, in biology, in science, and mathematics. But a little more concretely, this problem gets used by companies to decide who they hire as a first round interview screener. So there's one, they're an evil company, but there is one company that I know that uses this as their actual screener, and so I'm going to give you the trick to get past the screener. Okay, so our task is calculate the nth Fibonacci number. What is the obvious way to calculate the nth Fibonacci number in C? There we go. What's your name?
My name is Jan.
Jan, okay. I can't really see you, but we can still talk. So what is the most obvious way of calculating the nth number in the Fibonacci sequence in C?
The standard way to calculate the nth Fibonacci number is recursion.
Recursion. So it looks something like this. F of 1 equals 1, f of 2 equals 1. So you set your base cases, and then you calculate the nth Fibonacci number as f of n minus 1 plus f of n minus 2 with a recursive implementation. And then you get big O of 1.7 to the n. Okay, so here is fib1.c. Let me make it a bit bigger. I'm going to use long longs, which are integers with even more bits, so we can represent really large numbers. Which Fibonacci number do you want to calculate? Have a long set aside for it, and then have a base case. So for the first and 0th Fibonacci number, return 1. Otherwise, return n minus 1 plus n minus 2. You've seen this hopefully in lots of places, and if not, you should, at this point in the semester, know how to do that. So that runs in big O of 1.7 to the n time. Okay, what's the problem with that, Jan?
The problem is that the larger the n, the longer the time for the algorithm to search the nth Fibonacci number. Yeah,
the runtime's not good. So what should we do instead?
We could do memoization.
Tell me about the memoization one. That I put as fib2. Tell me about the memoization one.
Memoization is that you make a cache to store the value that you previously calculated. So each time, each calls of the recursive functions get less expensive.
Yeah, so we talked about this a bit earlier in semester. If you're calculating f of 4, then that means you're calculating f of 3 and f of 2. But if you're calculating f of 3, that means you're calculating f of 2 a second time. So why don't we just save f of 2 ahead of time, and then we don't waste our effort there. So let's look at fib2. And this is fib2. I have an array I have an array of memory. I'm going to set it to 0. And then each time I run my Fibonacci calculation, I'm first going to check if the memory for that nth Fibonacci number is set. And if it is not set, then I am going to, if it is not set, then I'm going to calculate it afresh and store it in memory. Otherwise, if it is set, I'm just going to retrieve it from memory. And I'll put these up for you. And then here at the bottom, you can just see that I've got an overflow detection mechanism as well to see if I'm going larger than long max. Okay. So that's our memoization technique. But that still has big theta that Hanju talked about earlier in semester. It has this tight runtime bound of big O of n with values stored in memory. But we have to then store big theta of n values in memory, so that's not great. So implementation 3, remind me the other method that we suggested that does away with some of this complexity. Jan? You suggested it before.
Oh, iteration?
Yeah, we could use an iterative approach to this, which is honestly a lot simpler. So instead of doing this fancy recursive thing, Fibonacci is nice because it teaches recursion to new students, but we probably don't actually need to do it. In fact, this simple loop is enough to calculate the nth Fibonacci number. Now, it doesn't have the benefit of the memoization one, so if we call it over and over again, it's still going to have to do all the computations, whereas in theory, we could store some of those memoized values in a file somewhere, but still not bad. So what about if we run the program 1,000,000 times with different values? Which of these should we use?
I think we should use iteration.
Well, if we want to run it 1,000,000 times, the cache, the saved memory that we have from the memoization is actually good, because even though it takes up O of n memory, we can actually store that O of n memory in a file and then read that file in, and then we don't have to do the computation over and over for the values that we've already stored. So if we're running this program over and over and over, probably choose Fib2, choose the recursive version that uses the memoization and store the results in a file. Or if you're actually being a little more clever, don't use recursion, use the iterative version, but also cache those values in a file as well. So you could take the memoization idea that's commonly talked about with recursion and just apply it to the iterative version. What, Jan, if we want to run this with really big numbers? Which of these versions should we use?
If you want to run it with big numbers, we should use with iterative version. Because
yeah. Why should we use the iterative version?
Because the iterative version doesn't use much memory.
Yeah. And more specifically, what happens if you'll remember our idea of the stack? Each time you do another recursive call, you're adding more data on top of the computer's stack, not like a stack that we've created, but the actual stack of the program. And so what happens is you can get a stack overflow if you do this too often. If you add too many stack frames, you're going to run out of stack memory, you get a stack overflow, and your program stops running. And at least 4 years ago, Stack Overflow was the most visited site on the internet for programmers because it was a place where you could ask any question and get an answer about a programming question. What happened in the last 4 years that changed this? ChatGPT, unfortunately. Which is actually, honestly, a bit of a loss because Stack Overflow also there was a very humane aspect to it as well. It was a place to interact with people. A lot of knowledge that ChatGPT now has was scraped from Stack Overflow. So it really is a bit of a loss, the fact that the traffic has gone down so much. Anyway, other than me bemoaning the past, if we want to do this with large numbers, we should really use Fib1 or 2. But still, we've got some limits. We've got longs. What if I want to run this with really big numbers? Jan, what should I do?
If you want to run it with really big numbers, if the size is too large, we could use the Binet's formula.
Yeah, we could use. Oh, wait! Don't. Yes, cheating. You're not meant to know about that. We'll pretend we didn't hear that. But If we want to do it with really large numbers, one thing that we could do is we could use this approximation formula that uses phi to the power of n. And so we can actually just compute f of n directly. The only thing is we're going to need big nums, which is another way of saying our integer size in C is limited. And so we're going to need some way of representing the numbers that are larger, and this gets complicated really fast. We can definitely no longer rely on the fact that integer operations are constant time-ish. And so Jan gave away one of the secret sources. So this is a really nice thing to surprise a programming interview with, is that you know that there's a closed form solution to the nth Fibonacci number given by Binet's formula over here, or Binet's formula. Don't know how to pronounce it. So let's look at fib 4. This is fib 4, and it's pretty simple. Run the calculation and produce the answer. So if you show this to the programming interviewer, they'll be both probably quite impressed and quite annoyed. So don't only show this version, but having it up your sleeve is a trick. So when they say, do a thing for the Fibonacci thing, and then you say, okay, I'm going to do it, and I will write it in 4 different ways with different trade-offs. They'll be like, ooh, she really knows what she's talking about. So that is the Binet's version. What is the runtime of it? Well, here we run into the problem with our model of computation, which is that arithmetic operations are not really O of 1, even when we're running them on integers, particularly exponentiation. And so this is going to become super important when we're dealing with really large numbers. And part of my early research was about writing programs that can deal with these really large numbers for the purposes of cracking codes using cryptography. So what is the most efficient runtime for Fibonacci in C with fixed size integers that we can get? Jan, what's the best program we could write?
I think it's O of n.
Which program would that be? Which technique?
It would be recursion with memoization.
Okay. Anyone else have a better idea?
If you disregard the arithmetic operation time, would it be O1 is the problem?
Well, we're not disregarding order of operations.
So, then
Iterative is ON, isn't it? Iterative is ON, isn't
It is O of n, but we want to do better. And Hanja is going to kill me now for showing you fib 5. This is the actual most efficient version of Fibonacci that you can do on C with fixed size integers. Let me pull this up.
Oh my god. Oh no.
So with C's fixed size integers, there are only about 100 Fibonacci numbers that are possible. So the actual correct solution to this problem is to write all the numbers in the file, and then when someone asks you for one of them, pull it out of the table. And so this is actually a valuable lesson. There is something really meaningful here, which is that the real solution to an algorithmic problem depends on your model of computation. It depends on the context around the problem. It depends on how many times you're going to use your solution. It depends on the actual computers in front of you. And this is what makes algorithms fun and interesting and exciting, is that all of these different elements combine to create computer science, to actually make it worth our time, spending our intellectual effort exploring this field. The main message from this class is that designing algorithms requires careful thought. What is the problem and what are your constraints? What are the theoretical characteristics of your solutions? What are the practical characteristics of your solutions? What actually happens in the business setting in which you're trying to do this, or in the theoretical setting in which you're trying to do this? And of course, the most important message, algorithms are fun. Thank you very much. When the data flows with repeats, arrays are teeming. Our code's big O time is seeming not as fast as KMP-ing. We could use linked lists, don't index, just append here. We could chase this pointer forever. Well, every pointer I point is a pointer to pleasure. I don't want to use AI. I just want to code in C for an H1 grade, and I'd print that in any string when all our trees are balanced too. You can use arrays and make a queue for an H1 grade, and I'd print that in any string. If the statement's true, our function is completing. And I'm wondering why it's so fleeting. If a segfault starts our screaming, then I debug X and Y's. Malloc has jumped its tether. I just hope my count accrues with a type that can measure. I don't want to use AI. I just want to code in C for an H1 grade, and I'd print that in any string when all the trees are balanced too. You can use arrays to make a queue for an H1 grade, and I'd print that in any string. I don't want to miss one semicolon. I don't want to miss one if. I want to see my proof go through with asserts like this. And I just want to sort your nodes. Your CPU, it ticks with mine. And calculate your float's exponent. The algorithm's fine. Yeah, 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 yeah. I don't want to use AI, everyone. I just want to code in C for an H1 grade, and would print F in any string when all the trees are balanced too. You can use arrays to make a queue for an H1 grade, and would print F in every string. We don't want to use AI. Alas, Shannon and Hanjev for an H1 grade, and would print F in every string where all the trees are balanced too. You can use arrays to make a queue for an H1 grade, and I'd print that in any string. I don't want to use AI. I just want to code in C for an H1 grade, and I'd print that in any string where all the trees are balanced too. You can use arrays to make a queue for an H1 grade, and I'd print that in any string. Thank you very much, everyone. Have a wonderful end of semester.